Helen Ogden used to be an ILAC postdoc in Warwick, and she's now a lecturer at Southampton. And she's going to talk about inference with approximate likelihoods.
Great, thanks very much, Christoph. So what we'll be talking about today will be work that I did while I was a postdoc at Warwick. So thanks very much to the ILAC project for giving me the opportunity to do that, and also for the invitation to speak in front of such an amazing audience. That's great. So what I want to talk about is a fairly simple approach to doing inference in models which have intractable likelihoods. And particularly, I'm thinking about the sort of situation where the likelihood is intractable because it involves some kind of high-dimensional sum or high-dimensional integral. And in that sort of situation, quite a common approach would be to say, okay, I can't actually compute this high-dimensional integral. It has no nice analytic form. So instead, I'll take some numerical approximation to the integral, which I'll just plug in to get an approximation to the likelihood. And then I could just forget about the fact that I've got an approximate likelihood and do inference using the approximate likelihood in exactly the same way I would have used the true likelihood if that was available to do inference. And what this talk will really be about is when is that a valid thing to do statistically. But I wanted to start just by giving a couple of examples of the types of models where you might use this kind of approach. So the first example is a very simple example of a generalized linear mixed model, which are a class of models I've looked at quite a lot, and they're also this kind of problem is really what motivated me to think about this more general problem in the first place. So my very simple example just supposes we have binary observations, which could be the pass-fail result of some test given to a load of school children, and the idea is that you expect children who are taught in the same class maybe to do their performance to be more similar to one another to students taught in different classes. So you want to allow for that dependence between the test results of children in the same class in the model. And one way you could do that is to say, let the log odds of that child J in class I passes the test be some linear combination of covariates, so that's the alpha plus beta xi part, plus this normal naught sigma squared random error term, which is shared between all children in the same class. So I'll call BI a random effect or a latent variable kind of interchangeably, so sorry if I don't use a very consistent language. So then we've got this very simple model to write down, and you want to do inference on the parameters of that model. So I want to do inference on alpha, beta, and sigma. And in order to do that, you want to write down the likelihood function for those parameters. That is, you want to write down the probability of seeing all the test results that you actually did, given a particular fixed value of the parameters. So it's very easy to write down the probability of seeing all the observations going the way they did if you're given the parameters and also given all of those latent variables, all of the BIs. Because under that assumption, you get that all of the observations are independent of one another, so that just reduces to a product of all of the terms for the individual observations. Unfortunately, these BIs aren't observed, they're latent, so what you could do instead is to find an integrated likelihood found by integrating over the distribution you supposed for the latent variables, which is just a product of normal naught sigma squared densities as you have there. So then you get this n-dimensional integral. It typically won't have a nice analytic form. And in general, n-dimensional integrals are not going to be particularly nice things to approximate, especially if you have a large number of latent variables, a large number of classes. In this one particular case, things aren't actually quite as bad as they seem. And that's because if you look at the integrand of the likelihood up there, you notice it's a factorization, and each of the terms in the product there just depends on a single BI, which means that you can in fact re-express this to be a product of one-dimensional integrals, one for each of the BIs. So you can rewrite it in that kind of form. And that means that in this one particular case, it's not so bad. It's relatively easy to compute very accurate approximations to one-dimensional integrals. But I'm just going to say more generally, you're not going to get that sort of simplification. So there'll be many other types of models where instead of each observation just depending on a single latent variable, it might depend on some kind of complex combinations of latent variables. And you'd no longer get this nice simplification where everything goes down into a product of one-dimensional integrals. So you really would be then stuck with that high-dimensional integral, potentially. So if we're not going to assume anything about the factorization into a product of one-dimensional integrals, what else could we do? Well, an extremely well-used approach in this situation is to take a Laplace approximation to the integral. So if I just write g of b and theta for the integrand, the idea of a Laplace approximation is basically to take an approximation to that integrand g, which is proportional to some multivariate normal density. And the quantities here, the constant and the mean and the variance of the normal approximation, are just chosen essentially to make the approximating g tilde as close as possible to the actual integrand g at their common maximum value. So first of all, you find the mean or the mode of the normal approximation to make sure that the mode of log g and log g tilde match each other. And then you find the variance matrix to make sure that the curvature of log g and log g tilde match each other at the common maximum. And then the constant is just chosen so that the actual values of g are the same at that maximum value as well. So it's kind of making them locally similar at that maximum value. And then given that approximation to g, you can just find an approximation to the likelihood by integrating over the latent variables. Since we've got an approximation which is a constant times the density, that just leaves the constant for the approximation to the likelihood. So that's relatively easy to compute. The question then is really, is it going to be any good? So first of all, it's very easy to compute, so that means that it's fairly well used in practical settings. So just as an example, if you wanted in practice to find estimates for this kind of model, you might go into R and use this LME4 package, which is used to fit generalized linear mixed models. So you have a response which depends on a covariate plus a latent variable, which is the same for all observations in the same cluster. We have binomial observations. You press go and you get some numbers. And you have a little look at the numbers, and we find here we have point estimates for sigma, alpha, and beta in this case. If I was kind of an applied researcher and I looked at these numbers, I'd probably just say these are probably the maximum likelihood estimates. But if I look a little bit more carefully about what the output says, up here somewhere it says these are found by using a Laplace approximation. So what they are, they're the estimates maximizing a Laplace approximation to the likelihood. And just from looking at this, I don't have much idea about whether these are going to be close to or far away from the actual maximum likelihood estimates, and whether the inference that I get out using the Laplace approximation is actually going to be have good statistical properties. Okay, so that's my first example. I wanted to give a slightly different example as well. So my second example is an Ising model. So it's just a simple Markov random field model. This time I have binary variables which I'm going to arrange on a big lattice, a big R by C grid. And just by convention, these binary variables are going to have values plus and minus 1 rather than 1 and 0. And the idea is that if I look at the conditional distribution of each variable, conditional all the others, that conditional distribution is only going to depend on the variables which are neighbours of the original one in the grid. So in particular, if I look at the log odds of an observation taking value 1, given all the others, that's just some unknown parameter beta multiplied by the sum of the neighbouring variables. So if all of the neighbours have value plus 1 and beta is a positive value, the variable itself is also more likely to take value plus 1, and so on. So it's a way of saying letting a variable be dependent on the values of its neighbours. So this writes down the conditional probabilities of each variable given all the others. If we want the likelihood for beta, we in fact have to write down the joint distribution of all the variables. And it turns out it's very easy to write down that joint distribution up to a normalizing constant. So it's very easy to write down the full joint distribution, except that won't be a proper probability distribution, it won't sum to 1. So we can say that the probability of taking value y is proportional to this function I'll call g of y and beta, which is just a product over pairs I and j, which have an edge between them in the grid. And the terms look like e to the beta times yi, yj. So that thing's fine, that's very easy to write down. The problem comes because the likelihood, which is exactly the same quantity, the probability of seeing the actual observed data given a particular fixed value of beta, to find that we actually have to find this normalizing constant, because the normalizing constant depends on the value of the parameters. So the normalizing constant, that just says sum up all possibilities for those unnormalized probabilities g. So it says sum g over all possible combinations of there's r times c variables, and there's each of them can take values -1 or 1. So there's kind of 2 to the r times c possible combinations to look at. So it seems like that's going to be a very nasty thing to compute. In reality, it's not quite as nasty as that. So by being a bit cleverer, it's possible to compute that normalizing constant at cost of the order the number of rows times the number of columns times 2 to the minimum of the rows and columns. So if, for example, you had a grid which had a very small number of rows but a very large number of columns, it would still be relatively easy to compute that normalizing constant. But if you have a very large square grid, it's still going to be very, very difficult. And you won't be, in fact, be able to compute this normalizing constant and therefore the likelihood exactly. So as before, what you might do instead is you might say, let's find some numerical approximation to that normalizing constant and plug it in to the g over z to get an approximation to the likelihood. There are lots and lots and lots of ways of approximating normalizing constants like that, so I just wanted to talk about one particular family. So yeah, rather than being a single approximation to the likelihood, to the normalizing constant, it's a whole family of approximations. And it's controlled by a tuning parameter, a positive integer tuning parameter, which I've called k. And the idea of that k is to say, as k gets larger, the quality of the approximation will increase, but the cost of finding that approximation will increase too. So to be a little bit more precise, it's finding an approximation to the normalizing constant for an r by c grid by looking at combinations of normalizing constants for k by c and k minus 1 by c grids, where k and k minus 1 are supposed to be a lot smaller than the number of rows. I don't expect it to be immediately obvious why this is going to be a good approximation, but you can see that it uses these approximations from these grids with a small number of rows and a very large number of columns, so it should be fairly efficient to compute. And in fact, just plugging into the formula from before, that means you could compute that at cost of the order k times c times 2 to the k. And if you think about k as just being a fixed constant value, and you're letting the number of rows and columns tend to infinity, then this is going to be kind of linear in the number of columns. And if we plug that approximation in to get an approximation to the likelihood and keep k fixed, then overall that approximation to the likelihood is going to have cost which is linear in the total number of observations in the grid, which seems extremely positive. The problem is, what happens, is that really a statistically valid thing to do? Is it statistically okay to say let's keep fixed and send the size of the grid off to infinity? Or really should we be saying how should we vary k as the size of the grid increases in order to make sure we do get statistically valid inference? Okay, so to sort of sum up the kind of common ground between those two examples, many models have intractable likelihoods because they involve high-dimensional sums or high-dimensional integrals. And one approach that you might use is to approximate that integral or sum, plug it in to find an approximation to the likelihood, and then essentially forget about the fact we made an approximation and just use the approximate likelihood as if it was the exact likelihood to do inference. And for this reason of kind of the fact that you're just forgetting about the fact that you made an approximation, I've called this thing naive inference with an approximate likelihood. Okay, so what might you do? If you had the likelihood, you might if you had the log likelihood, you might maximize it to find the MLE, the maximum likelihood estimate. If you have an approximate likelihood, you can maximize that too to find an approximate likelihood estimate. You don't know much about its properties yet. Similarly, you could, if you have a log likelihood, you can use that to find confidence intervals and test statistics in various ways. So one example is a kind of likelihood ratio type test statistic, an associated confidence interval where you basically just put all points in your confidence interval which have associated likelihood that's no more than a certain point below the maximum value, where that amount that you're allowed to go down depends on the nominal coverage of the confidence interval. You can do exactly the same thing if you have an approximate log likelihood instead. You can look at the maximum point and all points that are only a certain amount below that in terms of the approximate log likelihood. You get an approximate confidence interval. If you want to do Bayesian inference, you know that the posterior distribution is proportional to the likelihood times the prior. If we have an approximate likelihood, you can just plug that in instead, and you say we can have an approximate posterior distribution is proportional to the approximate likelihood times the prior. I'll just mention very briefly, this is quite strongly connected. In the case of my example 1, you have a Laplace approximation. This is quite strongly connected with Inler, which will be the subject of the next talk, so I won't say anything more about it than that. Okay, so we can find we can do inference in various ways. We can get out some output. What we're really interested in saying now is that output any good? So we might want to know, is the approximate likelihood estimator close to the MLE? Does the approximate likelihood estimator have some good statistical properties, similar to the ones that the maximum likelihood estimator does? Does the confidence interval with nominal coverage, 1 minus alpha, actually have coverage close to 1 minus alpha? Is the approximate posterior distribution close to the actual posterior distribution? Kind of intuitively, you kind of expect these things to have quite positive answers, provided that the error in the likelihood approximation is sufficiently small in some way. But first of all, we kind of have to think about what do we mean by error in the likelihood approximation? What's a meaningful error to look at? And then what do we mean, what condition do we put on sufficiently small? So to me, it kind of made sense to think about these problems asymptotically. So asymptotically as the amount of data is growing. And that's mainly because things like the second point saying, does the approximate likelihood estimator have good statistical properties? The kind of statistical properties I was thinking of were things like consistency and asymptotic normality, the kind of usual things that we know about the MLE. So I wanted essentially to be able to replicate those for the approximate likelihood estimator. So in order to do that, kind of first of all have to write down the kind of asymptotic setup that we're talking about for the MLE. And as was already mentioned, I think, in the first talk, quite a lot of these models that we're looking at that have intractable likelihoods, it's actually the asymptotics that you have are a little bit non-standard often. And that's because if you think about the most standard case for asymptotics, you're thinking about having kind of n independent and identically distributed replications or something like that. That's quite different to what you probably have in the settings with intractable likelihoods, because quite often they're intractable precisely because you have some kind of complex dependent structure. So you might no longer have any kind of independent replications going on. So I wanted to be a little bit more general in the kind of asymptotic setup. So instead of that, I just say, let's have some sequence of models and data indexed by n with log likelihood ln. And the idea is that then, as n grows, the amount of information available about the parameter in the data is growing too. So write theta hat n for the MLE for the nth model and data. And then I said I'm going to suppose the amount of information about the parameter grows as n increases. I'm going to suppose it grows at a particular rate, which I'll call Rn. So you could think of Rn as being some kind of effective sample size for the parameter. To be a bit more precise, if you write down what the observed information matrix is, so minus the second derivatives of the log likelihood, I'm basically supposing that that matrix grows at rate Rn. So if you were to divide the normalize the matrix by Rn and take the limit, then that would tend towards some constant positive definite matrix I of theta as n tends to infinity. So, okay, if this didn't make too much sense, but if it makes sense thinking about n IID replications, that's fine. It's the same kind of results that we get, just with Rn's in places of n's. So then what do we know about the MLE and likelihood inference? Well, we have that it's consistent. So if the model is correct for some value theta naught, then the MLE will tend towards that value in probability as n tends to infinity. And then secondly, we know that if we look at the difference between the MLE and the true parameter value and rescale by the square root of the rate, then that thing tends in distribution towards a normal distribution with mean 0 and variance matrix, the inverse of that I of theta matrix. To phrase that another way, it's basically saying that the MLE is kind of approximately normally distributed with mean theta 0 and variance, which is going down like 1 over Rn. Okay, so now we have our approximate log likelihood, and we're writing theta tilde n for the approximate likelihood estimator, which maximizes that. And the first questions that we want to answer is what kind of conditions do we have to put on the approximate log likelihood to make sure that the approximate likelihood estimate retains exactly those properties. So we want it to be consistent, asymptotically normal, and we want it to have exactly the same limiting distribution as the exact MLE. So that's saying we want it to be a completely efficient estimator. Well, I said before, it still seems to make sense to say we need to put some sort of, say that the error in the likelihood is sufficiently small. So we have to kind of think about what's a good way to measure that error. And the first thing that you might come up with is to just look at the error in the log likelihood. So I'm calling it epsilon n to be the difference between the approximate log likelihood and the true one. And it seems like maybe if that's sufficiently small, then we'll be okay and get all these properties. And in fact, that's true. So I found this in another paper which wasn't actually particularly focused just on this one issue. It was focused on showing these kind of properties for one particular kind of estimator, but the results carry across to the much more general case. So if we first of all suppose that the MLE does have these nice properties, we've got some sort of sufficient regularity conditions that allow that, and then if we say look at the maximum of that error in the log likelihood over the entire parameter space, and if that quantity grows less quickly than the rate, then the approximate MLE is going to be consistent. So that's good. We're saying we can allow this, this error to grow still with n, it just can't grow too quickly. Secondly, if that maximum of the epsilon error over the entire parameter space is actually going to shrink with n, then we get that it's asymptotically normal with the same limiting distribution. So there's a bit of a gap between those two. And in the meantime, in the ones in between, I suppose you might think that it will still be consistent, but the variance might be larger or something like that. So these are some results, but it's worth kind of stopping at this point to say, is this the best that we can actually do, these results here? And in particular, is this epsilon error, the error in the log likelihood, really the most sensible way to measure error in a way that's kind of statistically relevant? So to think about that, I came up with a little example, a little cartoon. So here, the dashed line is supposed to be the log likelihood that we can't actually get because it's intractable. The red squiggly line is supposed to be one approximation to the log likelihood we could use to do inference, and the blue approximation is another approximation. And the idea is which of these is going to give us inference that's closer to the actual likelihood. So to try and answer that, we might have a look at those epsilon errors, the error in the log likelihood. And we find that the blue approximation has a uniformly higher epsilon error than the red one. So it seems from that that perhaps the blue approximation is a kind of worse one. But if you just go back and look at what those approximations actually are, you see that the blue approximation is just the log likelihood shifted up by 2 units. And so because it's just shifted up by a constant, it's going to give you inference which is exactly the same as the inference you would have got using the log likelihood exactly. So that doesn't seem a very desirable property to have. So we have this situation that we want to get rid of the effect of shifting by constants. So the obvious thing to do then seems to be to differentiate this error. So we can do that. We can look at what I call delta n, which is just the size of the derivative of the epsilon n, so the derivative of the error in the log likelihoods. And sure enough, you see that the blue approximation now has 0 error in this measure, and the red one has much higher error. And what is this delta? Well, I said it's the derivative of the epsilon, the size of that. Epsilon was the difference in the log likelihoods. So it's the difference between the derivative of the approximate log likelihood and the derivative of the actual log likelihood. So it's the error in the score function. Okay, so having decided that, we can now get very, very similar results, but ones that are phrased in terms of the delta errors, the error in the score, as opposed to the original errors in log likelihood. So we get exactly the same result, but with deltas replacing epsilons for consistency. So we can say if the maximum of the error in the score over the entire parameter space grows less quickly than the rate, then we get that the approximate likelihood estimator is consistent. And then we get that if the maximum over the parameter space of the error in the score grows less quickly than the square root of the rate, then we get the other condition that it's asymptotically normal with the same limiting distribution as the MLE. So that one's slightly different. We're now allowing this rate to grow. It's just got to grow less quickly than the square root of the rate. Whereas with the epsilon errors, I had to insist that that thing actually tended to 0. This second condition still turns out to be a little bit of a problem in some applications. So you can weaken it a little bit further. It's a problem because of this taking the maximum over the entire parameter space. Sometimes you don't really want to do that. If you've got the consistency condition, then eventually it's enough to look in some small area around the true parameter value, because soon enough the estimator is going to end up there. So we can replace that by saying if, in addition to the first one, the maximum of theta in some small ball of some fixed radius t around the true parameter value, the same condition, then the same thing holds. That's just a sort of slight weakening that helps later on in an example. So we're not just interested in point estimation, which is all I discussed there, the properties of the MLE. We might want to do hypothesis testing, we might want to find confidence intervals, we might want to do Bayesian inference. So for all of that things, it turns out that you just need one more derivative of this thing. So I'm calling it gamma n theta, which is the size of the second derivatives of the epsilon error, which in other words is the absolute error in the observed information matrix. So let's make one more assumption that in this small interval around the true parameter value, the maximum of that gamma error grows less quickly than the rate. Under that condition, then all of the usual test statistics will have their usual asymptotic chi-squared distributions. And because of that, that's going to mean that confidence intervals using them will asymptotically have the correct coverage. And secondly, the total variation distance between the approximate posterior and the true posterior is going to tend towards 0. And actually, in practice, I found that this condition is to do with the error in the observed information matrix is a bit weaker than the condition that you have to show for the error in the score function. I'm not saying that's true in general, but just in the situations I've looked at. So this quite often tends to hold if the other one did. Okay, so if all of these conditions are met, I'll just summarize that by saying that the naive inference with the approximate likelihood is going to be asymptotically valid. Okay, so I have all these conditions now, so I want to go back to the examples that I started with and apply it in those examples. So first of all, let's go back to my latent variable model, my GLMM, on where I have m observations, m children, on each of n latent variables, the n classes. And I want to know when is inference that I find by using the Laplace approximation going to be asymptotically valid. Now immediately it seems like as the number of latent variables is increasing, I'm going to need that the number of observations per latent variable, that thing is going to have to increase in order that I'm going to get asymptotically valid inference. The real question is, does that number of observations per latent variable have to increase? Can it just increase at any rate? Or does it have to increase at some particular rate to ensure this is going to happen? And when this is really the type of problem that motivated me to look at this. When I first looked at it, I really thought, as long as this is increasing with the number of latent variables, everything's going to be fine. We can see on the next slide that's not true. So first of all, we have to work out what the rate is going to be, which turns out to be probably one of the harder parts of this. So in this particular example, if you think about as the number of observations per latent variable tends to infinity, eventually we're going to get a very accurate approximation of this combination alpha plus beta xi plus bi, because we have lots and lots of observations whose distribution only depends on that combination. So as we get one more extra observation involving that, the kind of additional amount of information gained from that is going to tend down towards 0. So that means that in this particular case, the rate that the information grows about the parameter is just going to be n, the number of latent variables. We can find all the errors. It's perhaps not too interesting. The only interesting part probably is that the error in the score function is of a lower order than the error in the log likelihood was. So you've kind of gained something by looking at that error in the score function. But when you put everything together, what you find is that if the number of observations per latent variable grows faster than the fourth root of the number of latent variables, then the Laplace approximation is going to give asymptotically valid inference. So it does seem then that the number of observations per latent variable really does have to grow at some certain rate in order for you to get good inference out. And just to check this, I mean, this doesn't say the opposite, right? It doesn't say that if the number of observations per latent variable goes slower than that, then you won't. So to check whether that seemed to be the case, I did a simulation study where I let the number of observations per latent variable grow at 3 different rates the middle solid line there is the n to the quarter rate. The line above is kind of n to the 0.3, and the one below is n to the 0.2 growth rate. And, well, I found various things. Let's just perhaps skip to that one. So this is coverage of confidence intervals, which was supposed to have 90% coverage. The three top lines are just there what happens if you use a very accurate approximation to the likelihood, which in this case is available to you because it's this model where the likelihood factorizes into a product of one-dimensional integrals. So they're all good. They're all close to the nominal 90%. The bottom three lines are what the coverage for the Laplace approximation looks like. So in the n to the quarter case, it goes along very nice and steady at around about 0.79 or something. In the case where it's growing more quickly than that, it tends up towards the nominal value of 0.9. And in the case where it's growing more slowly, only at rate n to the 0.2, the coverage gets worse and worse and further from its nominal value, which could be a real problem in practice if you were having confidence intervals that had coverage this far away from their nominal values. Right, so that's the first example I gave, the GLMM example. So let's go back to the Ising model example, see how this applies there. So let's suppose that we do have a square lattice. That's kind of the most challenging situation, it seems. So we have an m by m lattice. And the question we want to answer is, as the size of the lattice grows, as m tends to infinity, how should we choose that tuning parameter for the reduced dependence approximation to make sure we get asymptotically valid inference? Right, and it turns out that if it grows faster than log 2 of some constant times the number of rows in the lattice, then this naive inference with this approximation will be asymptotically valid. And it's perhaps helpful to rephrase this in terms of the cost of finding this approximation with this particular value of k. So we can do that and say that the cost of doing the inference with this approximation is going to be something that's less than the order m to this constant, depending on the true parameter beta naught plus 2. So I'll just show you what that constant actually looks like depending on beta naught. Okay, so if you have beta naught close to 0, corresponds to something quite close to independence, this constant term is very close to 0 too. So that means the order of finding asymptotically valid inference is very close to the order m squared, which is just linear in the number of terms in the lattice. So that's all good. As we get closer and closer to this particular value, about 0.44, the constant term just rockets up, gets higher and higher. This term here is the critical value for the Ising model, where the kind of whole behavior of the model suddenly changes. And in fact, behavior around this point is a little bit difficult because, in fact, the maximum likelihood estimator isn't even asymptotically normal for that particular value. So it all gets a bit strange about that. But nonetheless, this is kind of a big improvement that you've got a polynomial, asymptotically valid polynomial approximation scheme rather than this horrible exponential thing. So you make some progress by doing this. Right. So I just wanted to summarize and finish by giving a few kind of possible extensions to this, particularly kind of things that I'd like to discuss with anybody here a bit, since we've got this nice opportunity to discuss things. So the first thing, and this is something that I've been working on for some time now, is extending my example 1 to the generalized linear mixed model case. It turns out there's a few complications along the way when you're trying to do that. So the first complication comes with this rate that the information grows about the parameter. In example 1, that rate, I said, was just n, the number of latent variables for all of the parameters. It turns out that more generally, different components of the parameter vector can have different rates of information growth, which means that you can't actually apply these results directly as I've written them here. That's not too much of a problem because you can replace the scalar rate with a kind of matrix rate, and all the results are still quite similar. The second problem perhaps is a little bit more serious. The second problem is that all my results on the first line depended on you saying the actual MLE is consistent and asymptotically normal. And it turns out that for the general GLMM case, even that is not even asymptotic normality of the actual MLE is not a known result. I don't think it's a total disaster though. I think actually so in order to show the kind of error rates, you look at a series expansion for the log likelihood, and I think that having that series expansion and knowing how big the various terms are is actually going to be very useful in terms of showing that the actual log likelihood is kind of approximately quadratic, which is something similar to what you need to show that the MLE is asymptotically normal. So I think the same kind of results could be helpful. So it's not a disaster, it's just a bit of a nuisance. So secondly, I've talked about a couple of examples, but I think this kind of approach of finding approximations to the likelihood and then just using them as if they were the actual likelihood is probably used in quite a lot of settings. So I'd be very interested to hear from anybody who has ideas about those and how this kind of results could be applied. Thirdly, I've talked a lot about naive inference with an approximate likelihood, which is this process of just taking an approximation and then forgetting about the fact you made approximation, treating the approximate likelihood as if it was a true likelihood. Now, instead of doing that, you could acknowledge the fact that you've made an approximation and say, I know this isn't a true likelihood, but I'm going to use it, and make adjustments to your inference to cope with the fact that you've done that. So that's something that's quite similar to what's done when you're doing inference with a composite likelihood. So that applying those same kind of techniques here, I think could have some potential to improve the inference you get out using an approximate likelihood. And finally, something I think that's very interesting is something already mentioned a bit in this Ising model example, is when you have, instead of having a single approximation to the likelihood, you have a whole family of approximations. And what you would like to do is to choose between those approximations to do the inference. So you want to find an approximation which gives you statistically valid inference but doesn't cost you more than is actually necessary. As, for example, when I was choosing that parameter k in the Ising model example. And doing that in practice could be quite difficult. Even the example that I gave for the Ising model example, I sort of showed how the k should grow, but my choice of that was actually depending on the true parameter value beta naught, which is not actually tremendously practical. So good practical strategies for doing that which still have good theoretical backing, that would be really great. So that's a reference to the paper that covers most of what I've talked about, and that's everything, so thanks very much.
Any questions?
So this is a non-technical question, but in the simulation that you did with, to look at the coverage of confidence interval in the generalized linear or the random effects logit model, that's very clearly the software that I think most practitioners would use to fit that model. And with 8,000 students in the classroom, you still were very far away from nominal coverage.
Yeah. So.
Was there anything in particular about your example that made it particularly horrible, or is the software just that bad?
No, I mean, well, first of all, I think the binomial case is the binary case is definitely the worst one because you have kind of least information per observation. Secondly, my n here is quite big as well, so I've kind of, in some ways, I've had to go to quite a large number of. So we can look at this one here, perhaps. I've had to go to quite large numbers of latent variables before you actually start to notice the problem. So I'd say that I did have to work quite hard to find this. I mean, it's still worrying because people might still be using it with this kind of structure, but in a lot of examples that you look at in practice, there's not a huge difference. So it's not always as bad as this situation. I chose it to be bad.
I wonder if you knew how this C that diverges, you know, how it diverged or which critical exponent of the Ising model that represents. That's probably a bit of a...
I mean, I know the function for this C. I know what it. I don't know it, but I I know it. I don't really have much feeling for why it grows in this particular way. It seems to go with most things that everything goes bad around this critical value.
Is there particular exponents in the Ising model which have different physical meanings? And, my guess is this is related to what's called the correlation ramp.
Yeah, I don't know is the answer, but yeah, it could be interesting. Yeah, yeah.
Any more questions? No? Okay. Thank you, Helen.